Good morning. So this question is from NCRT Exemplar, and what makes this question special is the fact that you have involvement of a pentagon, a regular polygon. So the difficult part of this question is not solving the math of it, but drawing the diagram to find the direction of the electric fields at O. So what I've done is this is my origin, and I have shown the multiple electric fields coming towards O with the help of a diagram which you can see on the right hand side. Okay, so this is the diagram I have drawn. Okay, so you can see the diagram, and now I will explain you what I've done. Okay, and this is the most difficult part of this question, to find the angles which these vectors make with the axis, because that is where the resolution of vector will come and help us in finding the resultant vector, so to say. Okay, at O. Now if you notice, this is a regular polygon, and in a regular polygon the external angle is calculated by 360 degree by 9. So if you want to calculate any external angle, okay, so this will be 360 by 5 is equal to 72 degrees, and if you want to find the internal angle, this will be 108. The other way to find an internal angle is use the formula n minus 2 into 180 by n. So you can also find the internal angle, and if you notice, this will also come out to be 108 degrees. Right, the way I found this, I found the external angle, and then I did 180 minus the external angle, 108, and then I used this. Now if you notice, this angle is going to be what? It is 360 degree getting divided into 5 parts, so 72 degrees each. So if each one of them is 72 degrees, right, so the angle between all these vectors is actually 72 degrees, and if you notice, this angle being referred to is 18 degrees. Okay, this one, and this is again 72, so this is going to be 54. So this is 18 degrees, this is 54, so this is the split of 72 which is coming. You can always say that this is 54 and this is also 54, and the central angle is 108. Right, and similarly you can go on and solve this, and as far as this particular angle goes, right, which I said is 18 degrees, you can also calculate that very easily using some knowledge of trigonometry. I've used the concept of symmetry for this particular purpose. So this is 18 degrees, and this too by symmetry is 18 degree, and this is how much? This is again 54 degrees, 54 degrees, and this angle is 90. 54 and 90 is going to be 90 and 54, so this angle is 36. Right, we know this is 36 and this is also 36. So we can always find the how to resolve EC and ED, because the angles are 36 degrees each. So if you go to EB, for example, EB is 18 degrees, right? So you can do resolution of EB also in two parts, which is this and this. Now look at EE. EE again is at 18 degrees. You can do resolution of that also, and this is vertical, so you don't really need to do any resolution. Now if you get the angles, then what is left is analysis. Okay, so if you analyze, so first step in physics is to take control of the diagram, and especially in the case of resultant, take control of the angles. If you have clarity on angles, it becomes rather easy to solve the problems by the method of resolution, which is splitting the vectors in x-axis and y-axis. If you're not clear on how we got 18 degrees, you can do a bit of struggle and you will get this 18 degree value too. So it should not be that complicated, okay? Because this is how much? This is 72. So how much is the balance angle? 18. Simple. 90 degrees. This whole thing is 90 degrees. So let's look into the diagram now. If you notice, let me concentrate on EA, right? It is in y-axis. I really don't need to worry about it. And I know the distance from each of the charge to the center is R, and the side of the pentagon is A. And you can see, I can find this also. This is given to be R in the question. Okay, if you notice this, and even if it is not given, we can convert, we can get the value of R from the value of A, which is going to be the radius actually. Now let's come back. So EA is in y-axis. Let's look at EB. Okay, so EB has two components. If you see, EB is drawn like this. So I'll just draw the components of EB. One is downward, the other is leftward, right? So I know EB y and this is EBX leftward. Let's look at its counterpart EE. EE is drawn like this. If I draw this, the components is this and this, right? So this is E right towards the away, because the charges are positive, and then I split it. This is again 18 degree. I can easily find the perpendicular EE sine of 18, and I can find this EE cos of 18. Do you notice that for EB and EE, the horizontal components cancel each other and only the vertical, the sine of 18 degrees cancel. So due to these two, it's an upward electric field which is 2 times E. We can find the value of EBY or EE and sine of 18 degrees, right? And we know EA is downward, right? Downward, and we can write the magnitude straight away by calculating the perpendicular distance, right? So if you know that this is A side, this is A, and this is the base, so this is A by 2. So we can always find if this is our base, right? This is our base. We know the angles inside, so we can find the value of hypotenuse also, right? So it is something like this. So I know the base is A by 2 and this is my angle 54 degrees. So A by 2 upon hypotenuse is equal to sine of 54 degree, and my hypotenuse comes out to be A by 2 sine of 54 degrees. Okay, and that's the way it comes out, right? So you can always find this distance also, which is being used to calculate the electric field. So I'm doing analytical method. Let's look into the next one, D and C. So when I'm concentrating on D and C, if I were to see D and C, the values are 54 degrees. Okay, so this is 54, this is 54 degrees, right? We already know why, because we have done some calculations, and we understand that this is 72. These two angles are equal, so sum has to be 108. Each one of them is 54. So we can do resolution of both. Let's say I'm doing resolution of D. So one is upward, the other is leftward. Similarly for EC, if I do for EC, one is leftward, the other is upward. So these two cancel for EC and ED, and these two get added. So if I were to add them, I will write them as 2E and then of course sine of 54 degrees, right? So you have one which is absolutely down, and which is this. So we have clarity on that the resultant is actually just in the y-axis, right? And we know the distances. For example, we have calculated the distance of this perpendicular distance. We can find out, this distance, we have hypotenuse, we have found out. We know this perpendicular distance also from the same logic, that this is going to be A by 2, and if this base is known to us, then it's perpendicular divided by the base is equal to tan of 54 degrees. So the perpendicular is A by 2 sine 54. If we know the distances also, so we know the distance of this charge from here. So this, because this is a straight line coming, so we can find this also with the same logic as so let's say what is the distance of this particular, if you have to find, I can draw perpendicular from here, and so ignore what I just said. My logic was that the perpendicular length is going to be the same. It is not. In fact, this is the hypotenuse. So whatever is the hypotenuse you're calculating here, the same distance, right? So use A by 2 sine 54 as the hypotenuse value everywhere. So even the charge A from O is at the same distance. It's the hypotenuse. I shouldn't have taken perpendicular, but anyway. So if you were to write the values now, the values are pretty straightforward. If you were to write the values of electric field, so the electric field due to any charge in terms of the magnitude is given by KQ by the distance square, which is distance is A by 2 sine of 54 whole square, right? And then of course, this one is downward, so this is downward, or put a negative sign, and these are getting added upward. So I will just add them like numbers because they are finally just numbers in the same direction. So 2e sine 54, and of course I know e is again this, right? So you have two situations where you have upward and downward. You can see the value of sine 18 and sine 54 from the table, and you can do a resultant saying that the upward components are 2e sine 18 plus 2e sine 54, and then of course the downward part of it, which is e, only e, right? So I can just write e also, because e actually is kq by the square of the distance from the charge to the center O, right? I can put this. I have not put the values here. If I see the values of sine 18, sine 54, it is very simple for me to finally find the value of the resultant electric field at O. So this question is not difficult because the calculations are straightforward. I think what made this bit complicated is the figure. If you try to do this question on your own, you will realize that drawing the figure and then working on the angles is probably more difficult than calculating the electric field. So give it a shot, do it with your own hands, because seeing is believing, yes, but when you start writing it on your own, you start drawing the figure and marking the angles, you will see the degree of difficulty, and it will give you confidence if you do it on your own. Now let's say they remove in the part B the electric field at O if A is removed. Okay, so you have removed A. Now I will again do this analytically, so let's look at the B part. Now in the B part, the charge at A, which is here, is removed. So charge at A is removed. Okay, what changes? Which means then there is no downward part to it, right? So this will not exist. So when I write the resultant, nothing changes in the above calculation except the fact the resultant now is going to be only this part, because the net resultant is going to be only this, because you don't have anything downwards now. The x components have already cancelled with each other, so you're left with only this. Straightforward, right? So E due to A, this was due to A, is gone, so you don't need to write it. So the net resultant is upward, right, in the plus j direction. Let's look into the next part. In the next part it says the electric field at A is now replaced by minus q. Again, I will solve this analytically because it is becoming more of a vector question. If you notice the figure, right, which I've drawn here, okay, what will happen is we have already found out the x ones have already cancelled. Okay, so we don't need to really worry about them. Due to these two, the net x was coming out to be 2e sine 54, and due to these two, it was coming out to be 2e sine 54. So the two are getting added, and now at A, the electric field again is towards the A, which is upward, right? So you have 2e sine 54, you have 2e sine 18, and you have one more e which will get added. So if I just refer to this expression, the 2e sine 18 is still there. I have 2e sine 54, and then I have a plus ea, because changing the direction of q has to be done, because q has been replaced with minus q, and if it is a minus q, the electric field is towards the charge. And this is what I did. I just reversed it, and therefore I can add all the electric fields like numbers. Okay, so this was also straightforward, and why I'm able to do it so smoothly is because I got my diagram correct, and I'm able to solve for vectors very, very simply. Now let's say you have a different figure now, and you have to solve the same question now, but the change is now you don't have a polygon, okay, a pentagon. You have a regular polygon with each charge at the corner. So you hypothetically, for example, this becomes 9 sides, these become 11 sides, and so on and so forth. So it's a regular polygon. It could be a hexagon, 6 sides, so on and so forth. So I think what changes probably is the angle, right? And of course the number of charges which are getting added finally, right? So if you see these, if you see a pentagon, for example, we had the 4 charges playing a part in the upward direction. So if I just draw a regular polygon let's see, can we solve the same with some analogy and with some logic which is of some value to us. If I use, say for example, I can't draw n sides, but I will draw something which is regular and maybe larger. Okay, so let me try that. So I draw something which is of some, you know, so this is, I've drawn this, and let me take this to using the principle of, so I draw this, and then I draw, so this is it stops here, and then it takes another route, right? So somewhat rough figure, but the effort is to try and draw a larger polygon with more sides to it. Okay, so let's say these are symmetry and this is the center, and these are the charges. So the electric field, so this is 1 2 3, okay, and this has not come out really nicely. If you notice, I could have drawn it in a better manner, but anyway, so I'm just trying to correct it so that it looks slightly better than this. So you have 1 2 3 4 5 6 7 8, sides. So this is, what I've done is I've drawn a octagon now, and if I were to look at an octagon, this is my electric field number A, this is B, this is C, I'm sorry, it should have touched here, this is D, this is E, this is another one, this is another one, and this is another one. So these are the numerous things I get of an octagon, and the overall, if I notice 1 2 3 4 5 6 7 8, right? So I have 360-degree getting split into 8 parts. So this is 8 fours are, and then you're left with 40, so 45. So each of the angle is 45 degree. Even if I calculate an external angle, which is 360 by 8, comes out to be 45, and the balance, which is the inner angle, is 135, right? So this is 135, so we're referring this to be 45 degrees. This is 135, so half of that is 135 divided by 2 is equal to 2 6 are 67.5. So this is 67.5 and this is 67.5, right? So each one of them is 67.5, okay, and this angle is 45 degrees. Again, the approach, the strategy to solve the question is, because I know it's a vector, it's important for me to worry about directions. Okay, so I'm just worrying about directions to start with, and then it's an octagon, so a lot of symmetry available to me in terms of an octagon, because if I draw perfect octagon, for example, which I'm not here, it will give you an insight as to what is happening. Okay, for octagon, let me just try and make it in a better manner, so maybe I'm able to do this time. Okay, let me just restrict myself to a hexagon, for example. Okay, let's say I draw a hexagon. Okay, 1 2 3 4 5 and 6. So let me just draw the symmetry. Okay, and then we will draw some inferences analytically. So if you notice, this is a hexagon, and by symmetry itself, if it's an even-sided figure, right? So an even-sided figure, you can see most of the electric fields are getting cancelled. Doesn't appear because my figure is not a great figure which I've drawn, but logically speaking, if you place on a circle, you have points which are equally spread, then they're opposite to each other, because this angle, this is a shorter side which I've drawn, should have been somewhere here, and this would have come directly opposite to it. Okay, so if this is your genuine figure, and I will rub this off so that it's clear to you. If I draw correct hexagon like this, then these two are opposite to each other, and these two are also opposite to each other, and so is the case with these two. Okay, this has not come out to be as nice as I would have thought it would, but I'm trying to draw something better than this. So you have this figure now, and let me just rub something off. Point I'm trying to drive home is the fact that if it's a regular even-sided figure, okay, and let's see if this looks slightly better than this one. Okay, this is bit better. Okay, now if you notice, everything is symmetrical. Okay, And that's a point. If you don't see symmetry, you don't cancel. Now this vector and this vector cancel, this vector and this vector cancel. So my conclusion is, if you give me an n-sided polygon, which is having even number of sides, my resultant is going to be 0, because by symmetry. Okay, but if you give me an odd, shaped, which means the number of sides are odd, not even, then this is 1. So like, let's look at, we drew a pentagon, right? In a pentagon we were able to find some resultant. And similarly, if we are given a polygon which is 7 sides but is regular, okay, all the sides are equal, then we will get an answer. Now how will that answer change is with respect to a pentagon is what we need to discuss. So let me try and draw. So I just made my life easy. I just picked something from the Wikipedia, and I'll show you what happens in a case of a heptagon. So 7 sides. You've seen for even number of sides, the resultant is 0, right? So we've seen for hexagon, if it's an even number of sides, the resultant is 0. So let me just show you this. So look at, you have a charge here, electric field is here. So if you notice these two electric field, the x will cancel. You will get answer in y for both of them. If you see this one, again the x components will get subtracted and the y components will get added, right? If you notice this one, okay, and I take the components which are in x and y, for example, this component, and I take one more, the x components are cancelling, and then there is y component, and then of course this is straightforward downward. So you can see that in a regular heptagon also, the resultant in x does not exist. Very similar to what we did in the case of the pentagon, right? So if you have an odd shaped figure, x does not exist but y does exist. Obviously the magnitude is going to be different because the angles we're dealing with is different. So in the pentagon you calculated sine 18 and sine 54. In the case of a heptagon you will not see those numbers, but you will definitely see a lot of y-axis components coming up. In the case of a pentagon, what you saw was you had 2 components which were these in y, then you have 2 components more in y, and then a component which was downward. In this particular case you found these 2 components getting added up, then you had the 2 components coming from here and here getting 4 components, and then 2 components downward and 1 more component downward. So 7 components, out of which 4 are upward and 3 are downward. In the case of pentagon, if you notice, you had around 4 components which are upward but only 1 component downward, right? So you can, on a very simple note, say that if you're given an n-sided polygon with even number of sides, the resultant at O is going to be 0. But if you're given a n-sided polygon with odd number of sides, the answer is going to be what? It's going to be a y-axis directed electric field, and you will have to do those cumbersome calculations which you did for this, right? So this is the explanation, okay? And just to summarize, please draw correct figures, label them, and analysis requires that you are able to analyze something, and the best way to analyze is a picture. So first draw a picture, analyze the picture, and mark angles. We're dealing with sines, so angles, vectors, all of this is very important. Understanding the resolution, which is getting cancelled with which. And then of course you need to be a bit logical in, for example, I was able to break the code that in the even shaped scenario, the resultant is going to be 0. So much for your NCERT exemplar problem number, whatever we did. And please follow my channel. You will find some excellent videos on for JEE Mains, NEET examination, on CBSE State Board, or any part of the world you are. Even if you're preparing for IB Board, you're preparing for IGSC A level, or you're preparing for AP Physics, all of stuff is available here. And I've started adding chemistry and maths also, which I used to teach. I used to teach maths. Chemistry is new to me, but I have done all of this myself. I'm just trying to recall and adding a lot of chemistry videos also. Thank you very much for your time today. I hope you enjoyed this video. If you did, please don't forget to subscribe to this channel, and do mention the comments section if you want more. Thank you.